Great. So can you hear me?
Yes.
Okay, great. Thank you so much. Today I'm going to talk about our recent work on learning optimal classification trees, strong Maxwell formulation, which is a joint work with my advisor Phoebe Vianas and Andres Gomez from University of Southern California. To start with, let me freshen your mind like a little bit on classification trees. Like classification trees, like one of the machine learning methods for doing classification. So here we have an example where for a homeless person, we want to decide if we should assign them a housing type 1 or housing type 2. At each internal node of our tree, we perform a binary test. So if we pass the test, we take the right branch. If we fail the test, we take the left branch. And we have a bunch of these tests at different internal nodes. And at the end, we take a path and we get to the leaves where we have a prediction there. So the goal is to design the tree, including the test to perform and the labels to assign at the leaves so that we maximize the prediction accuracy. The literature on decision trees can be divided in two parts. In the first one, we have traditional methods, such as the famous CART or C4 algorithm. They are like heuristic. At the other hand, we have models using mathematic formulations such as mixed integer programming for optimal decision trees. In mixed integer programming formulation for decision trees, we have modeling power where we can include different constraints such as fairness to the problem. On the other hand, we have the ability to provide guarantee on the optimality of the solution that we find. But these methods, these MIP methods, they're not as fast as heuristic ones such as CART, where they don't have the modeling power. So, but the reason that these MIP methods are not good enough is that they have weak LP relaxation. So in this work, we are going to strengthen the relaxation of the MIP models to improve their performance. Okay, so let me talk about the formulation of our problem. To start with, I'm going to talk about the data set that we have. So we have a classification data set, including data points where each data point has a feature vector X, and also we have a label for each data point yi. And the goal is to come up with a classification that we can predict the labels for each data point. So we have a binary decision tree in this form in our problem, but we add two dummy nodes to our formulation. One is the source node, which is connected to the root, and the other one is a sink node, which is connected to every node in our tree. So the goal is to come up with a flow problem. So that's the motivation behind these two dummy nodes. So in our problem, we have, beside the source and sink, we have internal and terminal nodes. So at each internal node, if we have two options, either we branch or we predict a label. So we stop growing the tree. If we branch, so for example, here in node 3, we branch on a feature, then we cannot go to the sink directly. So this edge is prone. And then so we have a test. If the data point has a feature value of less than 1, which is the threshold, we go left, otherwise we go right. But if we predict a class, then technically we prune the rest of the tree, so we cannot branch, and the next step is going to the sink. So here, using the decision variable W, we have a prediction for node 3. And then at the terminal nodes, we always predict a label, but if we have pruned the tree earlier, so it means that we have a prediction at one of the ancestors of that terminal node, then we don't do anything with that terminal. Now, if we fix the structure of the tree, by the structure, I mean the feature that we branch on the node and also the prediction that we have, then what we want to decide next is to find a path from the source to the sink for each data point. So that's the problem. And finding this path from source to sink is technically, from source to sink is technically like a flow problem. We formulate it as a flow problem. And then the last decision variable in our formulation is z, which this decision variable is 1 if the data point I take the edge between node n and m prime. So we're using this decision variable to imply the flow conservation constraint. So any data point that enter a node should leave that node through one of its children. Okay. So in our paper, we showed that the formulation that we have has a stronger LP relaxation compared to the approach OCT, optimal classification trees. And also in our computation later on, we showed that we have a improved performance, so we are 7 times faster. Now, as I mentioned earlier, if we fix the structure of the tree, including the branching features and the predictions, the goal is to find a path from the source to the sink. So this idea, there's a nice thing is that we can decompose the problem into a Bender's decomposition approach. So in the master problem, we fix the structure of the tree, the features and the predictions. And then the remaining what we have is that for each data point, we solve the max flow problem that I mentioned. And in this problem, we decide if the data point is correctly classified or not. If yes, then we're good. If not, we have a violated constraint that we need to add it back to the master problem. And then we iterate until we find the optimal solution. And here in this Bender's decomposition, instead of solving the max flow, we take the dual of max flow, which is a mean cut problem, and then we move on. So by doing this, we show that we have like an improvement in the performance, which is really suitable for larger data sets. Now, in order to solve the mean cut problem, instead of solving it like traditionally, we have a tailored algorithm, which is really fast. And the idea is that for a given data point, we look at the tree that we get. If there's a path from the source to the sink for this data point, then we can cut anywhere through this path to find the mean cut. But if there's not such a path, the idea of finding the mean cut is that here we see that at node 1, we take the right branch. So any other arcs connected to this node would be part of the mean cut. So we traverse the tree from the source to the sink, and in this way we can find all the cuts in the mean cut, all the arcs in the mean cut. Okay. And an important observation here that we have in the Bender's decomposition is that all the cuts that we add to the master problem in this algorithm are facet defining, in a sense that all of them are necessary for defining the convex hull of the MIP feasible region. So they are never dominated. Okay, so let me get into the numerical results. So we compare our approach, which are like the flow OCT and also the Bender's decomposition with bin OCT, binary optimal classification trees, and OCT. So we solve this problem on different data sets from UCR repository, and then with different depths. So when we look at this result, what we see is that in a given time, our algorithm Bender's is able to solve more instances compared to OCT and bin OCT. And both the flow OCT and the Bender's are like faster compared to the optimal classification tree approach. And here in this diagram, what we see is that we have this ability to prune the tree. So we have early stopping approach. So here we see that again, vendors and Flowcity outperform OCT. So we can solve more instances. And at the last graph, what we have is that we will look at the optimality gap. And if you notice, as we increase the size of the problem, OCT and Bean OCT tends to have bigger optimality gaps compared to vendors and Flow OCT, which means that we can maintain a smaller optimality gap compared to the other approaches. And these are the references that we had in this presentation. And thank you for your attention.